Okay. So, today we are in this particular class we are going to discuss about the equivalent one dimensional motion or one dimensional problem for a central force field. The description of the problem is as follows. If you recall, the basic Newtonian differential equation of the motion was r double dot minus r theta dot square is equal to f of r, right. Now, if you remember, we also had L equal to r square m r square theta dot, which means theta dot is equal to L by m r square. Now, if you substitute for this particular term, then we get r double dot plus r into L square by m square r to the power 4 is equal to f r, or r double dot is equal to f r minus L square by m square r cubed. Now, this right hand side of this term, right hand side of this equation, we have two terms. One is the actual force which is due to the central orbit, and one is a term which is L square by m square r cubed, which also is proportional to the distance, but it is not a real force. It does not have the components of real attractive or repulsive forces in it. Instead, what we have here is a term which consists of angular momentum and mass. Now, please remember that except for simple harmonic motion, simple harmonic oscillation in one dimension, every time an object moves under a central force field, there is a angular momentum which is constant. For the special case of one dimensional simple harmonic oscillation, this angular momentum L is equal to 0. So, except for that particular case, whenever a particle is moving under the action of a central force field, there is this term, and this term is also, if you understand, L is positive, m is definitely positive. So, L square by m square by r and divided by r cubed, it is a term which will contribute to the right hand side of this equation, irrespective whether the motion is, if it is a slow movement or is a fast movement, does not really matter. This term, because angular momentum is a constant, it does not matter if it is if the particle is passing through an epicidal point, if the particle is passing through some sort of minima or maxima, does not matter. Everywhere this term will be omnipresent. Okay. So, we can write an equivalent force term which we denote by f dashed r. Please note that this is not the derivative, it is just a representation of the entire right hand side. We can write this as f r minus L square by m square r cubed. So, that is this is nothing but the equivalent force, right. Now, if there is an equivalent force present, there will also be an equivalent potential present. Okay. So, if we write an equivalent potential V dashed of r, which will be V of r plus L square by m square r square. Now, how is this related? F of r, or rather f dashed of r, will be minus d dv, because it is a single variable function v of r. Okay. Check that. The first term will give you the standard force, okay. Minus dv dr will be the first term, which is the standard force term due to the presence of central field. The second derivative, the second term under, if you perform this derivative, will give you L square by m square. There is a minus term coming up and it will be r cubed, which is exactly equivalent to this term. So, now for a moment just go back to this one particular equation, E is equal to T plus V. So, T, which is half m V square, is equivalent to E minus V, right. This V square will have one radial and one transverse part associated with it, and we have already seen that the transverse, if we only take the radial part, that is r dot square, that will be equal to this particular force term. So, we can substitute for this one and we can write this as half m V r square, which will be equal to E minus V effective. Okay. So, we are just, what I am doing is, in this kinetic energy term, there will be a contribution from the radial part and one contribution from the transverse part. We have already seen that if we can rearrange the transverse part, because that has a theta dot term associated with it, to give this particular type of force. So, what we are doing is, we are just writing this V r, which is nothing but r dot square equal to this. So, from this we see r dot is equal to 2 by m E minus V effective, V effective being this, or actually we can write this as V effective, this will be easy to visualize. Okay. So, r dot is equal to root over of 2 by m into E minus V effective whole root. Yeah, I said root over once, so that is fine. Now, if you look at this effect, I mean, if you look at this particular form of equation, does not it look like a equation of motion for a velocity component for a one dimensional motion, as if the motion is, I mean, if you recall, this V effective is also a theta independent term. V effective, the first term is the standard potential, which is already theta independent by definition. The second term is this L square by m square r square. So, we have included all the theta dependence into this particular term, and we converted the theta dependence into an r dependence term. So, as if the motion under central force field can essentially effectively be described by this 1D description of the problem, where the only velocity is only variable is r, which is changing as a function of t, giving rise to velocities and acceleration, and the motion is taking place in an effective potential, which is given by this particular expression. Now, right now we are not specific about the form of VR. I am saying, I am making a statement for a very general force field, which has a which can have any form of potential, which is given by this particular term. So, let us be general and try to see. So, right now we are not sure about the functional form of V effective. We know that one term will be L square by m square r square. Okay. Now, this term, if you examine carefully, at r equal to 0, this term is divergent, okay, and r equal to infinity, this term gives you 0. So, whatever may be the functional form of VR, we do not know a priori. There are possibilities that the effective potential will look something like this. So, this is V effective and I am drawing R here. Please understand, I am not specifying 0 energy level here. Right now, I am just trying to be very general. I am not specifying 0 energy level. So, I am not drawing the vertical x axis. I am just marking this as y axis as V effective, and I know that we know that R is being plotted here. Right. it, as I said, it can have this particular form, it can also have very different types of form, we will come to that in a moment. Now, let us assume that the particle, the total energy E of the particle, which is also a constant of motion. So, once it is, if we choose the initial condition according, I mean a set of initial condition which will give one specific value for energy, we can always find another set of initial condition that will give a different value of energy E. So, E is something that in principle can be controlled from outside, okay, and that depends a lot on how the thing starts, because it is a conservative force field. Once you set energy, the initial energy, the energy will remain constant throughout the motion. So, let us assume a situation where we have set energy at this particular level, let us call it E1. Now, the this energy, I am just taking the intercept of energy, this energy value with this effective potential. The point, we call it R1. Now, let us assume another energy value. Let us say we lowered the energy value to a level which is given by E2. Now, this interception, let us say the R value is R2, for this one let us say it is R3, this one let us say it is R4. Now, for these two cases, for energy E1 and E2, let me try to give you a brief account of how the motion in a general, in this force field, how could be the motion, a general description. Examine the case E equal to E1. Energy is sufficiently high. What I mean by sufficiently high is, see, there are some ups and downs in this potential, but the particle which comes with an energy E1 does not see all this. The energy is too high, so energy stays here. Only time, so essentially what I am trying to tell you is, if energy is at this particular level, then this particle does not feel that there are ups and downs in this potential. So, it directly comes to the close to the force center. R, this straight line, this vertical line essentially marks R equal to 0. So, it is R equal to 0 means it is a, is the origin of the force. With this energy, it tries to come close to the origin of the force, and essentially it intercepts this effective potential at the point R equal to R1. And because the potential below R equal to R1, the potential is higher, the particle cannot come closer than R equal to R1. Now, what happens afterwards? Afterwards, it will, so the motion of this particle with energy equal to E1 will be bound between R1 and infinity. It can go anywhere without any bound, because assuming that the potential stays in this particular level, okay, it will not have any further interaction with the particle, will have any not have any further interaction with this particular potential except for this point. So, and beyond this point, it cannot, the particle cannot come closer to the force center than R1. So, if we try to draw a very quantitatively the trajectory of the particle, this is my R axis, okay, and the trajectory will look something like this, okay. So, the particle comes from infinity, the shortest distance of approach becomes this distance, which is given by R1, and then once again it moves away from the force center to infinity. Once again, I am not, specifying the shape of this curve. It could be, I mean, we do not know the law of force at present. So, we cannot comment on this particular type of orbit, but all I can tell you that this is an unbound orbit. So, the particle essentially comes from infinite distance, the shortest distance of approach is r1 and it again turns back and goes to infinity. So, it is an example of unbound orbit, and this particular phenomena is called scattering. Scattering in central force field is a very well studied and very well observed phenomena. For this particular course, we are not going into the very deep of scattering phenomena, because it is slightly advanced topic. We have to consider many other parameters for that. But I am let me tell you that the first few experiments to which was the pathfinding experiment to determine the structure of atomic structure and all. So, these are all scattering experiments. Rutherford experiment was a scattering experiment. Stern-Gerlach experiment, okay, not Stern-Gerlach exactly, but Rutherford experiment was a classical example of scattering experiment. So, this is one situation when we can have what we call scattering. What happens for energy equal to E2? What happens is, okay, please understand that there are two very distinct regions. One region is if the particle comes from infinity starts coming from infinity, then with energy E2, then it can come only as close as R4 from the force center, not closer than that. Okay? Because if it comes from infinity at r equal to R4, it will have an interaction with the potential, and beyond R4 potential goes upwards. Okay. So, it cannot cross this barrier, because it has an energy E2 which is not sufficient to cross this height, jump this height. The energy will be short, I mean it cannot come, if it comes from this side, it cannot come closer than R4. So, if the particle comes from infinite distance, then it will once again be a scattering, but this time instead of R1 we will have R4 here, but it will nonetheless it will be a unbound orbit, and we will see another scattering. Okay. What happens if somehow the particle ends up in this domain between R2 and R3? Okay. Now, how does it go here? We are not sure about it. Maybe it starts, the initial condition is such that it starts somewhere in this, between this R2 and R3 two bounds. Okay. That is a possible explanation for this. But whatever it may be, once it is inside this well, potential well, where with energy E2, that means it will have two interceptions R2 and R3, it cannot go beyond that. Please understand that we are discussing classical picture here. If it is a quantum mechanical picture, in quantum mechanical picture tunneling is allowed. I think you are all familiar with this term. We have all studied particle in a box, particle in a finite potential wall and all. So, there we have seen if the potential is finite, then we can have tunneling, especially in this type of cases, but because it is a classical picture, tunneling is not allowed. So, there is no tunneling. So, either the particle stays beyond R4 or it stays between R2 and R3. Now, if it stays between R2 and R3, these two are the turning points, and if you look back to this equation which was written as R dot equal to 2 by m E minus V effective, okay, whole root, at these 2 points, okay, actually not only at these 2 points, any point where E and this potential has an interaction, this particular term becomes 0. So, that is why R dot becomes 0, and R dot becomes 0 means, as I discussed during the discussion of epicidal point, these are the turning points. So, that is why we have turning point means where the velocity, radial component of velocity vanishes and the particle goes from changes direction from this to that. So, this is a turning point, this is a turning point. Similarly, R3 and R4, all these are turning points. So, how many turning points we have in this picture? We have one turning point which is given as R1, another turning point which is given as R4, and we have two other turning points, one is at R2 and one is at R3, right. So, we have, now let us focus only on this particular case when the particle is bound between the limits R2 and R3, that is to say it is bound to move within these two turning points. Now, what happens to its motion? We have already seen that the unbound orbit which results in a scattering with the turning points either R1 or R4 depending on the energy. What happens for bound state is we have the particle keeps moving between two circles with radius R1 and R2. So, let us say this is my, so this radius is R2 and this radius is R1. Okay. So, the particle will move between these two in this manner. So, I do not think it is a very clear picture. I will try to draw it once again. Please excuse me for this. So, we have R1 and we have R2. Okay, I will just draw R2 a slightly bigger, that will help us drawing it clearly. Okay. So, R1 and R2. Okay. So, if the particle goes like this, then it comes back like this, goes like this, it comes back like this, like this. So, if it goes like this, comes back, goes back, like this. So, essentially the motion is confined between two circles of radius R1 and R2. But please recall that R1 and R2, although it is a bound state, bound orbit, it is not a closed orbit. So, this is a bound orbit but not closed orbit. So, this is an example of a bound orbit, but this is not a closed orbit. What is the meaning of bound orbit? Bound orbit means where the maxima and minimum distance from the center of force is fixed. It cannot go beyond the maximum distance or it cannot come closer to the minimum distance. Now, what is the meaning of a closed orbit? A closed orbit is the orbit that traces itself over and over again with time. So, that what I mean is, now if we drop this general description and try to describe a bound orbit under the action of inverse square law of force, then we know from our previous discussion that the only possible bound orbit is an ellipse. Of course, circle is also possible, which is also is a special case of ellipse. Now, in an elliptical orbit, what happens is force center is one of the foci, either this or that, and this is my r, this is my theta. Okay. So, the particle keeps moving on this elliptical orbit over and over again. So, this is my R min and this is my R max. So, these two are the bounds for this particular orbit, R min and R max, and at the same time an elliptical orbit under the action of a central inverse square central force field is also a closed orbit, because it remains the same over time. So, it remains, I mean, it traces itself back over and over again with time. So, that is why the planet in planetary motion, each planet will come back to its previous position exactly after a certain period of time. Of course, it is again, it is only the first approximation, it is a closed orbit, it is not exactly closed, because we probably know that from modern day astronomical observation, it has been seen that each planet, the orbit is deviated every year, or every single evaluation the orbit is deviated very slightly. That is due to all other nonlinear effects, all other forces that is acting on the orbit. But we are not bringing that into question. From purely classical calculation point of view, this elliptical orbit is a closed orbit, because it is not only bound between these two limits, but it will trace itself over and over again. So, we have seen that in general, in a central force field, we can have a scattering motion or we can have a bound motion, which will provide a bound orbit, but not a closed orbit. Now, tomorrow or in the next class, what we are going to do is, we are going to focus only on inverse square law of force and see how does the equivalent potential picture looks like, and we will try to describe the motion in central force field in as per the equivalent one dimensional motion picture. Thank you.